Uh-huh. Okay, so now what we have here in front of you you see, when we do demonstrations, aesthetics is very important. I do not claim that I'm very clean and nice and elegant here, but you have to do things with a sense of jamaliyat. You have to do it aesthetically. Otherwise, the impact will not be that much. Okay, so now what we have in front of you is this is an electromagnet. And there's a coil in here, and these are pole pieces. These are magnetic material, and the field goes like this. You produce a field like this. Okay, a field goes around like this. When this coil is energized, the current goes through this. So it's a C-shaped electromagnet. C. Okay. Now inside this electromagnet, we pass a current through the coil so that the electromagnet is energized and there's a field. And inside this, I have a disc. This is a metal piece, a disc, a circular disc, and it's like a pendulum. This goes around the electromagnet. This oscillates inside the magnet, and it slows down slightly. So it just oscillates in a normal fashion. The electromagnet is not yet energized. So now what I would like to do, while I set this into motion, I would like to energize the electromagnet. So I am attaching the wires of the electromagnet with my power supply.
Magnet. उसको अटैच
Alright, this is set into oscillation. I'm going to turn on the voltage. And as I turn on the voltage, it immediately comes to a halt. It was oscillating. As soon as current passes through the electromagnet coils, it immediately comes to a halt. Let me do this again. So there is some current that goes through this, about 2 amperes. It energizes the disc and it immediately comes to a halt. This is called magnetic braking. With the help of, now I think now you can explain why this is happening.
Eddy current.
Once again, eddy current. Because now you have a disc, a metallic disc that is going through a field. That field through the disc is changing. Currents are produced inside the disc that are circular, and they will try to oppose the motion of the change of field, which means that the magnet would not like the disc would not like the field through it to change, so it would like to remain steady. And the equilibrium position is to be steady in the ground state, which is at the lowest position of the pendulum. So that's why this object comes to a sudden arrest. This is called magnetic braking. So electromagnetically you can brake objects. You can make magnetic damping. Instead of viscous damping, which would happen in a normal pendulum, this pendulum is going to come to rest anyway. That's viscous damping. But with the help of a magnetic field, you can make it brake immediately. Let me do this once again. Here you go. The current is 1.6 amperes. The field would be around 300-400 Gauss, I think, to this electromagnet at this point. Now I'm going to change this a little bit. What I'm going to do now is, I'm going to change this disc into something fancier. Now I would like to have a disc like this, which is corrugated, which has these slits built into this disc. Okay? Right now we have a solid disc. So I'm going to take this disc out. Okay, so now this is the disc with the corrugations inside it, with the interruptions to the flow of electric current, which means currents will have a high resistance. We'll see a high resistance, so the currents will be smaller. And now if I oscillate this disc, right from Alright, so now this is the normal, this is the disc with the corrugations inside. Alright, now I'm going to turn on the current, the same amount of current. It's 1.3 ampere and it has not been damped. It's 1.5, 1.6 ampere and it's still not damped. The same amount of current, even a larger amount of current, does not damp this object. The reason is clear. Now the eddy currents have a larger resistance because the area through which currents can flow is smaller. They are intercepted by air, by tracts of air, by gaps of air. So the current is smaller, the loop of the current is smaller, the magnetic field is smaller. Right? So now we have arrested the eddy currents by putting it in transformers using laminations. Laminations in transformers reduce the eddy currents. Eddy currents are unwanted unless you would really like to have braking. So let's perform this experiment one last time.
Excuse me.
Yes.
Those protrusion that are disturbing the oscillation. Why do you have them? Why does it have to be?
Why do we have these gaps?
No, the protrusions that are disturbing the oscillation of the disc. Those protrusions.
These gaps?
Partitions.
Not gaps.
The partitions?
Not
Yes.
Yes, those are.
Yeah, tell me.
Why do they have to come out that much? Why not?
Okay. So you see, there is a magnetic flux is continuous. So this steel, these pole pieces have high permeability. So the flux is concentrated to these pole pieces. So if you would like, if these are close together, the field is going to be larger. If these are further apart, then the flux is going to come out of the pole and is going to spread. And when it spreads, the flux lines per unit area is going to be smaller, so the field is going to drop. So if you would like to have larger fields, you would like to have the poles come closer.
Because I can see that they are disturbing the oscillation. That's
Oh,
all.
okay. So no, we need these poles to have a strong magnetic. Let's perform this experiment one last time. Okay, it's oscillating. I turn on the voltage. The current is large, 2 amperes. It's still not damped. So this is a vivid demonstration of how eddy currents actually help. So I think we are out of time. This is all that I had to show, and after half an hour break, inshallah we'll have presentations from Islam, from Hassan, and from myself. Yes. Okay, thank you.